Hello? Okay. Hi everyone, my name is Anjali. Sorry for the technical difficulties. We thought we were going to have a projector, but it doesn't look like it's connecting, so I'll just be talking and hopefully that doesn't compromise the quality of the presentation. No, that's fine, I got it. Thank you. Okay, so I'm going to be talking about mathematics in Sanskrit and how it connects to various other fields. Alright, so when ancient mathematicians and poets and all those people were doing research in mathematics and working on it, they needed to find a way to express large numbers in a compressed way in verse. Because the way they talked about the work that they were doing was through poetry. So they didn't write long proofs like you'd find in a math textbook nowadays. It was all compressed into verses. So there was the challenge of how do you put large numbers into poetry with fitting the meter and everything, but still conveying the information that you need. So they had a system called the Karpayadi system, which encoded numbers using the letters of the Sanskrit alphabet. So the first step to understanding the system is figuring out how the Sanskrit alphabet is organized. So the way it works is that there are 25 main consonants: ka, kha, ga, gha, nga, cha, cha, ja, jha, nya, ta, tha, da, dha, na, ta, tha, da, dha, na, and pa, pa, ba, pa, ma. So these 25 consonants are actually organized based on where from the mouth they're produced. So the first line, ka, kha, ga, gha, nga, if you say them out loud, you'll realize that they're all coming from the same part of your mouth, from your throat. The next line, cha, cha, ja, jha, nya, all come from the back of the mouth. If you say them out loud, you'll realize that they're all produced from back here. Then ta, tha, da, dha, na, all come from the top of your mouth or your palate. The next line, ta, tha, da, dha, na, is all from behind the teeth. And then the last line, pa, pa, ba, pa, ma, is from your lips. So all of these are carefully organized into a very logical system. So then when they wanted to encode these numbers using the alphabet, what they did was they wrote out all the consonants going across 10 in one row, 10 in one row, and then the remaining 5 in the next. So each letter was given a value from 1 through 9 and then 0. So ka got 1, ka got 2, ga got 1, ka 1, ka 2, ga 3, ka 4, nga 5, cha 6, cha 7, ja 8, cha 9, and nya 0. So, I don't know if you can see it here, but I have a table. So the first row going across is ka, kha, ga, gha, nga, cha, cha, ja, jha, nya, and all of those correspond to 1 through 9 and then 0. Then the next 10, ta, tha, da, dha, na, ta, tha, da, dha, na, all it's the same thing, 1 through 9 and then 0. And then the remaining 5, pa, pa, ba, pa, ma, got 1 through 5. And then there's another set of letters, the semivowels, ya, ra, la, va, sha, sha, sa, ha. Okay. Those are 8, so each of those gets 1 through 8. Ya got 1, ra 2, la 3, etc. And then all the vowels get 0. So that way every letter in the alphabet is assigned a number. A couple more notes on the system. If you have a mixed consonant, two consonants, one after another without a vowel in between, like in the word ma, da and ma come after one another without anything in between, then you only look at the value for the second consonant or the third consonant, as it may be, in that syllable. So if you look at the word bhakti, the kta syllable at the end, you only care about the ka doesn't matter. And then another final note is that when you're looking at these numbers, they wrote them in reverse place order. So if they were writing a word or phrase that corresponded to the number 100, instead of putting a letter for 1, a letter for 0, and another letter for 0, they did 0, 0, 1. So the place orders are reversed. So this system was extremely versatile. They used it for a lot of different stuff. One big thing that they did use it for was to encode the value of pi in verse. So there was a 15th century treatise called Karana Paddhatihi by Pudumana Somayaji, and in this book he gave the value for pi based on the circumference and diameter of a circle. So the verse that he has is Anunna nunna nanunna nityai samahatas chakra kala vibhaktoho chandamsu chandradhama kumbhipalay vyasastadardham tribamaurvikasya. So what this basically says is that for a circle of diameter, anunna nunna nanunna nityai, it has a circumference of chandamsu chandradhama kumbhipalay. So these long words actually correspond to values for the diameter and circumference of a circle. So considering the first one, anunna nunna nanunna nityai. So the first syllable is a. A is a vowel and corresponds to 0. Then there are 9 nas one after another. Anunna nunna na na nunna ni. So those are 9 nas. And na corresponds to 0 because it's in the second row. Ta, tha, da, dha, na. ta, tha, da, tha, na. So na is 0. So we have 1 0 for 9 zeros for all the nas, and then the last syllable is tyai, which is tya, which is a mixed consonant, so we only care about the second one, which is ya, and ya corresponds to 1 because it's ya, ra, la, va, sha, sha, sa, ha, and ya is the first one in that row, so it's 1. Okay, so this long word we have 10 zeros and a 1, and then because of the place order reversal it becomes 1 followed by 10 zeros, which is 10 billion. So that's how they gave us the diameter of the circle that they're considering. Then for the circumference they gave Chandamshu Chandra Dhamakumbipale, because I don't have my slides for you to see. Hopefully you can take it for granted that this means 31,415,926,536. So the letters correspond to these numbers. So then what do you do if you're given the circumference and diameter of a circle and you want to find pi? Well, the relationship between those two values is circumference equals pi times the diameter, so pi equals the circumference over the diameter. So when we divide these two numbers, we get 3.1415926536, which is pi accurate to 10 digits in the 15th century, which is pretty impressive. So this system was used for long after that. In fact, in the book Sadratnamala, written in 1819 about astronomy, the author Shankaravarman gives another value for pi accurate to, I believe, 17 digits, using the phrase Badhram Buddhi Siddha Janma Ganita Shradha Smaya Bhupagihi. So if you look at these letters and do the Karapayadi system on them, you get 3141592653589799324, which is pi accurate to 17 digits in the 1800s, and it's been encoded really neatly into this big verse. So the Karapayadi system is not useful just for mathematics, it's also been used in music. So if, the Carnatic music system has 72 Melakarta ragas, which have all the notes in the scale. So that's sa, re, ga, ma, fa, da, ni, sa. So the way these work is that both the sas and the fa in the middle are fixed. Those are constant notes across all 72 ragas. But the other 5 notes are variable, and you can actually use the Karapayadi system to figure out what those other 5 notes are. So if we consider one of the Melakarta ragas, Dhira Shankara Bharanam, the rule says that the first 2 consonants of the raga name encode the raga number. So if you look at Dhira Shankara Bharanam, that's Dhi and Ra. So Dha is 9 because Ta, Tha, Da, Dha, Na, Ta, Tha, Da, Dha. So Dha is 9, and Ra, Ya, Ra is 2. So, but then because of the place order reversal, it's 29. So Dhira Shankara Bharanam is raga number 29. So the first part of figuring out the notes, ragas 1 through 36 use ma 1, which is a lower ma, and ragas 37 to 72 use ma 2, which is a higher ma. So Dhira Shankara Bharanam falls into the first half, so it uses ma 1. Then the next step to finding the remaining 4 notes, you subtract 1 from the raga number and then divide that by 6. So 29 minus 1 is 28, and then 28 over 6 is 4 remainder 4. So both the quotient and the remainder are important. So the quotient of 4 corresponds to a value of Re 2 and Ga 3, and remainder 4 corresponds to Da 2 and Ni 3. So what they've done is basically organized the options for Re and Ga into a fairly logical table that corresponds to the different possibilities for a quotient when you divide by 6, 0 through 5. And they've done the same thing for remainders of 0 through 5 to find the values of Da and Ni. So basically in this way they've organized the entire all 72 ragas using the Karapayadi system in a very logical and systematic way, which is fascinating because you don't think of music as always being so intrinsically and closely related to mathematics, but in our system both of them are very closely linked. So another final application of the Karapayadi system is to encode dates. So a lot of the time, instead of very obviously saying when a book was written, the author will encode the date in the end of the book. So in the case of the Narayaniam by Bhattacharya, it ends with the phrase Ayurarogya Saukyam, which means long life, health, and happiness. So this can either be interpreted as just a regular benediction that you find at the end of a work like this, but if you look at it with the Karapayadi system, it actually dates the completion of the Narayaniam. So if you look at the phrase Ayurarogya Saukyam, the first syllable is A. A is a vowel, so it has a value of 0. Ayu, which is Ya, corresponds to 1. Then Ayuraru, so that's 2 Ras, and Ra is 2. So we have 0, 1, 2, 2 so far. Then Gya, which is a mixed consonant again, we only care about the second, which is Yas, that's a 1. Then Saukyam, Ya, Ra, La, Va, Sha, Sha, Sa. So Sa is 7. Kya, again we only care about the second consonant there, which is a Ya, so 1. So then, reversing the place order, we get 1,712,210 days after the start of the Kali Yuga is when the Narayani was completed. So if you assume that the Kali Yuga began in about 3100 BC, that dates the completion of the Narayaniam to about 1586 AD, which is around when other texts refer to it having been completed. So this is a really cool and efficient and sort of subtle way that they use to encode a lot of information in a non-obtrusive way. So aside from the Karapayati system, there are a lot of other ways in which mathematics was incorporated into seemingly unrelated fields in the ancient world. So one of these was poetry. Poetry was not just, like, in English literature, I guess poetry is just pure art, but in Sanskrit, a lot of it was also very logically and organized. So Sanskrit meters use two kinds of syllables, short and long, laghu syllables and guru syllables. The way a lot of poetry is organized is that there are 4 quarters to each verse, or 4 padas. And the number of syllables in each pada can vary from as little as 4 to as many as 26, and apparently there's a theoretical limit of 999 syllables in a pada. So the most common meter is Anushtup, which uses 8 syllables, and a lot of the Bhagavad Gita is actually written in Anushtup. So because of this, you have a lot of different options for organizing different kinds of syllables in a certain fixed amount of space. So poets who also happen to be mathematicians, because they were capable of doing so much at the same time, wondered about how many combinations they could fit into this fixed space using just 2 kinds of syllables. And the work that they did on this actually led to the discovery of the Fibonacci numbers by the linguist Hemachandra in 1050 AD, which was actually a couple of centuries before Fibonacci discovered them. So maybe we should be calling them the Hemachandra numbers after all. So just again, as another example of how they managed to condense so much information into such little space, we're going to consider one meter called Bhujanga Prayatam. So the way they defined a lot of these meters is that they'd give the meter name and how it worked in the meter. So they'd have a verse written in this meter with the meter name and then the definition of the meter all in one verse, which is so compact. So for Bhujanga Prayatam, one line from the verse that defines it is Bhujanga Prayatam Chaturbiryakare. So what this means is that the meter Bhujanga Prayatam has 4 yas. So the way they talked about the meters and the organization of short and long syllables is that they had letters that corresponded to triplets of short and long. So 4 yas means 4 triplets that are called ya. So the ya triplet refers to a short syllable, a long syllable, and a long syllable. So when they say 4 yas, they mean that the meter Bhujanga Prayatam for each pada is short, long, long, short, long, long, short, long, long, short, long, long. And if you look at the phrase where they say this, Bhujanga Prayatam Chaturbhiryakare, that's actually short, long, long, short, long, long, short, long, long, short, long, long. So they've defined this meter using the meter, which is really cool. So if you want to clap it out, Bhujanga Prayatam Chaturbhiryakare. So you can see that it is really 4 short, long, long, short, long, long, which is pretty cool. So I have a couple of verses for you to really get a feel of the meter, which is pretty cool. So the first one is from Tulsidas. Namami Shamishana Nirvana Rupam Vibhum Vyapakam Brahma Veda Swarupam Nijam Nirgunam Nirvikalpam Niriham Chidakasham Akashavasam Bhajeham. So you can see that it has this short, long, long, short, long, long. And the nature of the meter actually is that it gives it this flowing feel, which is really nice for devotional poetry because it doesn't stop, it has this continuous feeling. And Adi Shankara also used this in a verse in praise of the river Ganga, which goes, Namaste Sturange Tvadanga Prasanga, Bhujanga Sturanga Kuranga Plavanga, Anangari Sanga Sabhanga Shivanga, Bhujanga Dipangi Kritanga Bhavanti. So you can see that it has this rolling rhythm, which even though Bhujanga Prayatam actually means gate of the snake because it has this wavy feel, it also really helps in this verse talking about the river Ganga because that sense of flow is also conveyed. So it's really interesting how this mathematical system, I mean, it's really a lot like binary if you think about it because it's short and long syllables, but while maybe in the West they've used it for computers and stuff, we used it for poetry and things that, in my opinion, maybe are a little more beautiful than just machines. So I think they did a very good job of using mathematics for a lot of more beautiful stuff. Thank you for listening. I hope you enjoyed. If you're interested in seeing my slides because you didn't get to see them due to technical difficulties, you can just come up to me afterwards and I'll probably email them to you or something. Thank you.
If people who signed up, they have their email address, can you send us a copy? Can you send it to them? Huh? Can you send it to Ajit? We will share it. So, ये पंचीकरण कृतवन्तः, if you have given your email address